Okay, so sorry for the interruption there. First part of this lecture wasn't recorded. But so reminder of what we were doing. We have a surface. We want to do chop it up, add it up on a surface as we're looking at little pieces of flux. We realize that we can understand the surface better by viewing it as an image through a parameterization. We talked about parameterizations in the past. Recall, furthermore, this is a situation we've already written some things down in. We've already sort of got a certain amount of setup in surface parameterizations. Recall specifically on the what I like to call the large scale, we have this thing called the capital N vector. Right? Capital N was computed as this cross product, xu cross xv. Recall that pointing in that direction, the unit vector pointing in that direction, we've called little n. That's our unit normal vector for that surface. It's all ancient history. We did this a couple weeks ago, maybe, or at least a week ago. I forget. On the small scale, what I like to call the differential scale, again, old news. We had these two vectors, xu du, xv dv, whose cross product allows us to compute this area ds. ds computed by that formula. Again, this is all done before, right? Ancient history. And the observation I'm making now, this is the last thing we did before we switched back here to this screen, is that these two things happen to be equal. Capital N du dv is the same as little n d capital S. The reason being that both of these things are equal to, for their different reasons, both of these things are equal to little n, capital N magnitude du dv. Okay, reminder of why ds is all of that. Capital N is that. Okay, everybody on board? I think we're back up to where we were a few minutes ago. So these two vectors, capital N du dv, little n ds, are of interest. The most immediate reason that we can see as to why we care about these is because we care about this thing, little n ds. Let me remind you again, going back, why do we care about little n ds? Well, because what we wrote here for flux, f dot little n ds, we wrote this down thinking of it as sort of integrand and differential, but we can reconceive of this as that being the integrand, that being the differential, and then look at what I got in there. What is my differential? It's little n ds. It's this thing, little n ds. And what I've seen now is that is, in fact, also capital N du dv. Everybody on board? So this vector, little n ds, actually is really a very natural thing. Coming back up here, just looking at our big picture, I like to think of it as, in fact, more natural to break up this expression with little f on the one part, and then little n d capital S on the other part, because, and I've made this observation in other contexts, everything over here in the what I'm calling the differential comes from the piece of surface. This comes from the piece of domain that we're looking at. That's determined by the domain. And everything that I've got in green here does not come from the domain. Everything that is in green there is very reasonably what you might call the integrand. It's what's interacting with the domain to make the object in question I'm interested in, namely flux. So this is really a pretty natural way to break things down. That in mind, I'm going to give this thing a name. Right? I suppose we don't have to, but this is a really common choice to make. I think this is a really good choice. This thing, little n ds, capital N du dv, if you prefer, I'm going to call it ds vector. Oh, let me, blue, yeah. I'm going to call that the ds vector. Again, for pretty natural reasons, this ds vector tells you everything relevant about the little piece of the domain. It tells you how that little piece of domain is oriented, right? The way that vector points, the way the ds vector points is telling you about the orientation, however it might be, of the piece of surface. The magnitude of ds, the ds vector, is telling you about the size. How big is this piece of area? How much area is there? Magnitude of the vector tells you that. You can see both of these facts directly from these formulas down here. Okay, very natural thing. That having been the case, or that having been observed, right, these nice facts about the ds vector, we can rewrite our flux integral. Again, we have this new kind of a Riemann sum here. This thing, it's great to have new Riemann sums, but again, if you can't compute them, it's just an exercise, right? So we can rewrite that thing with these facts in mind. Little n ds, capital N du dv. Alternatively, we can think of it as our ds vector. And so our flux formula rewrites it, and you can have any of these three different sort of optional perspectives on how to compute your flux. Flux is that integral, or that integral, or that integral, depending on your situation and your sort of needs. Yeah.
Why does the orientation matter?
Yeah, because it matters because that's how you keep track of whether the vector field is moving along your surface or through your surface, right? If the fluid is flowing like this, here's your surface. If your fluid is flowing like this, there's not a lot of flux. If your fluid is flowing along like this, there is a lot of flux. So how the surface is oriented compared to how the fluid is flowing has to matter.
No, but aren't there like two normal vectors to that surface? So there is like one pointing up and one pointing
Yeah, well, no, that's quite right. That's a good point. So note that the direction that the normal vector is pointing is the direction that I want to consider to be the positive direction through the surface. Right? If you want to talk about how much fluid is flowing through the surface, are you trying to keep track of to what extent is the fluid flowing that way through the surface, or to what extent is the fluid flowing that way through the surface? Right? Are we trying to figure out, are birds leaving the reserve, or are birds flying into the reserve? So they're fundamentally different. Yeah. Right. Okay. All right. So again, these different formulas have different advantages. Let me walk you quickly through the different advantages of these different points of view. This one is the one that's most naturally relatable to flux. Right? We motivated this notion of flux from the point of view of component times area. That's just the easiest way for this particular application. As it turns out, what happened to be convenient for our purposes, this is the one that was easiest to motivate. On the other hand, that's hard to figure out how to compute that. That's not something that we have existing formulas for, but this is. Everything here is in the pullback. Everything is a function of u and v, and you can just flat pull it back and plug and chug. This is a double integral. Plain old chapter 14 style double integral, du dv, iterated integral, that is. Crank it. And that's really nice. The advantages of this are that it's very compact. It's easy to write down. Right? Less pencil lead. Less finger movement. Right? You save calories writing that down. So this is my favorite notation for that reason. It's very compact. Also, it's fundamentally natural because this is telling you everything that's involved in this calculation that relates to the surface, and this is telling you everything that's involved in the calculation that's not directly coming from the surface. So it's really mathematically very natural to write it like that. Okay. All right. So we're in shape to actually crank out some calculations. There is one quick concept that I want to give you before we start running, and that is just to be careful about one little aspect of parametrizing. Parametrizing a surface is not exactly like parametrizing a curve. There is one thing that's different, as follows. I'm going to remind you about how we do curves. Here's a curve. All right, and if I have a starting point there, and if I have an ending point there, and if I say parameterize that curve in that direction, okay, And you would just make sure to parameterize it in that direction. Whatever parameterization you write down, you can just think through, hey, which way is this going? Hey, what happens as t increases? Am I going the way I'm supposed to be going? Or perhaps am I parameterizing this the wrong way? In which case, whoops, silly me, I have to reparameterize. I parameterized it backwards. Okay. All right. Here's what's, so I'll say it this way. It's very easy when you're parameterizing a curve. It's intuitive to tell if you're parameterizing it the right way or the wrong way. Okay. For comparison purposes, suppose I have a piece of surface. If you parameterize that piece of surface, and let's suppose it's understood that this piece of surface is oriented that way. So in other words, I'm trying to figure out to what extent is the fluid flowing, upward, you might say, through the surface, as opposed to downward, I suppose you might say, through the surface. That being a given, that being the oriented surface we're interested in, if you parameterize it, how do you tell if you parameterized it the right way or the wrong way? You can't just think about the parameters u and v and, as u moves in this direction, as v moves in that direction, and think about, it's really hard to think about where the orientation even comes from. Right? So you have to recognize that you don't have orientation intuition when you're parameterizing surfaces, like you do with curves. With curves, it pretty much leaps off the page at you whether you parameterize the right way or the wrong way. So we have a new problem to deal with surface parameterizations. Did I parameterize it the right way, or did I parameterize it backwards, the wrong way? Am I counting fluid going upward as required through this surface, or am I inadvertently, accidentally computing how much fluid is going downward through this surface, which was not what the question was? Okay. It's no big deal. All you have to do is that when you parameterize, when you come up with your parameterization, realize that from that parameterization, you can compute xu, you can compute xv, which will then give you your capital N as xu, that's a u, cross xv, and you can look at your capital N and you can just directly see, look at your capital N and ask, is it pointing the correct direction? Is it pointing the same way as the given orientation of the surface? Or, very possibly, because I have no good intuition for this, could it possibly be that I inadvertently, parameterized this thing with a normal vector going that way, which is the wrong way? It'd be like the analogy would be like, if you parameterize, with a parameterization there, and, when you go ahead and compute, remember t, your tangent vector up here is, x prime divided by the magnitude of x prime. If you compute that, you have to worry about, is it pointing the right way, as it should? Or, if you weren't paying attention, maybe you parameterized it backwards. In which case, whoops, we're going to get the wrong answer. Everybody see the analogy here? Okay. The good news is it's really easy to resolve. All you have to do is just look at your resulting capital N and just see, is it going the right direction or is it going the wrong direction? Now, with that said, let's go ahead and get our hands dirty. We'll see this bear out in a calculation. Here we go. Let's suppose I have a fluid flow given, and I have a surface given. Notice this is an oriented surface. This is not just a collection of points. This is a collection of points, the part of this paraboloid sitting over the unit disk, but oriented a certain way, oriented downward. So when I ask to compute the flux, what I mean by flux is how much fluid is flowing downward through this surface. Downward in this case is what I want to consider that's the direction of flow that I'm interested in. Maybe I'm interested in the extent to which birds are flowing into my reservation as opposed to outward from my reservation. There's a sign. I've got to decide which is the positive sign, and this is the what I'm calling positive in this case. Did I see a hand somewhere? Yeah. No. Okay. All right. Okay. So now again, here's where students very reasonably. Want to just plug and chug? I get it. Right? And in fact, that's largely right. We've got our f given to us. We can compute from the parameterization. We can compute that capital N with standard formulas. Pretty much, yeah, plug and chug off to the races. Right? Here's our formula for flux. Flux, sometimes written like that, comes from a parameterization with this formula like that. And take a deep breath and plow very largely. Here are the details. We do have to parameterize our surface. I'm going to use the graph parameterization. We talked about graph parameterizations back when we were computing scalar surface integrals, computing surface areas, masses, that kind of thing. So I just, the big idea here is if z is let's see if I can zoom out here. If z is a function of x and y, then that pretty much tells you your parameterization. This is what gives me that, as you can see right there. Okay, so I parameterized. Quick acknowledgement. Look at the two possibilities here. Did I just parameterize the right way, perhaps? Or maybe, inadvertently, did I just parameterize the wrong way? It's really not obvious based on looking at what we've got here. I've got a formula for it, but is that the right way? Is this the wrong way? Right? Got to worry about that possibility. Okay. So here's where you got a heads up. Let's look at what was given. The surface was given as oriented downward. Right? Oriented downward. Now what does that mean? I'm going to draw some pictures here. Whoops, see, I hit the wrong button. Let's come over here to here's our surface. Oriented downward. That doesn't even sound right. Can you orient something like this downward? I mean, at a point like that on the surface, downward isn't an optional of orientation. The possible orientations both have to be perpendicular to the surface. Here you might say are your two options for orientation. And while neither one of those is pointing exactly downward, only one of them is in any sense pointing downward. Right? So, in fact, let me draw a better picture of these orientations. Keep in mind, an orientation is a collection, really, of normal vectors. It's a notion of perpendicular through the surface combined at all different points. That collection of green vectors you might think of as being one of the possible orientations. This collection of blue vectors, all of which are the negatives of the green vectors, of course. You might think of this as being sort of the other option. And I appeal to your, sympathies. Man, those are complicated. Right? How would I describe all of those green vectors? Well, golly, there's a lot of them. They're pointing all different directions. How would I describe these blue vectors? Wow, there's a bunch of them. They're all pointing all different directions. We have a nasty task of how to actually, with perhaps one or two words, with a simple English phrase to describe everything about the directions that these orientations point. It's not realistic. So, because of the intractability of the problem, we start to get realistic and we ask, not can we give a perfect description of the directions, but how can I at least distinguish between the two possibilities? And again, you look at these vectors, all the blue vectors are pointing at least a little bit somewhat upward. All the green vectors are pointing at least a little bit somewhat downward. So rather than being precise, which is impossible, we're going to distinguish between these with this kind of admittedly sloppy distinction. I'm going to refer to the green orientation as being downward and the blue orientation as being upward. Is everybody on board with that? It's an imperfect, but sort of a best solution in a situation where there's no perfect solution. Right? So let's not let perfectionism be the enemy of progress, as I think the saying goes. Right? Yes.
So what if you have like a sphere?
Great. Fantastic next question. So it's context dependent. So in this case, for that surface, a reasonable way of distinguishing between the two different orientations, for example, might be upward versus downward. Here's another thing you might do. I'm totally getting to your question. Another thing you might do in this case, you might say, I think this would distinguish between blue versus green here, toward the z-axis versus away from the z-axis. Right? You say either one of those, and it's perfectly clear whether you're talking about the blue one or the green one. Yeah? Okay. So she asks then, what about a sphere? If you have a sphere, well, let's draw the orientations. Here are the two options. And here, if you were to say upward versus downward, that does not help. Some of the blue vectors are up, some of the blue vectors are down. Some of the green vectors are up, some of the green vectors are down. If you say upward versus downward, that's not helpful if you're talking about possible orientations on a sphere. Right? So think about a different sort of, shared distinguishing characteristic that would helpfully distinguish between this green set and this blue set. And I would suggest inward versus outward here. Yeah, that would be, toward the origin versus away from the origin would also work just fine. Yeah.
So just going back to the question, would you say that the green is the downward?
Yeah, the green for this one here, that green orientation there on the paraboloid, I would say downward is a very helpful way to describe it. Yeah.
If you said like outward though, would you come to the same?
I mean, outward has the ever so slight problem with saying outward in this case is that the surface is not technically enclosed, and so. But I think people would get it, right? It would be a quibbly complaint to say, technically it's not outward of what, So I would prefer downward or toward or away from the z-axis, but none of this is going to be perfect. Okay, so that's what we mean by these bits of language. Now let's look at our current situation. We are oriented downward, it says. That means this downward means that we're looking at this green orientation. Did I parameterize, let's get rid of this distraction here. Are my normal vectors that I've computed here, are they going the right direction or the wrong direction? And check this out. That z component's positive. Right? So, inadvertently or otherwise, let's see here, did I draw a, no. As it turned out, because I couldn't sort of visualize this coming, I parameterized this with a capital N vector that is pointing at least somewhat upward, and that means I inadvertently created the blue orientation. And again, it's really hard to see this coming, right? I mean, it's on a curve, you can just straight up see whether you're parameterizing one way or parameterizing the other way. It's really hard on surfaces. Okay, so what's the difference? How do you deal with it if you parameterized it backwards? In this case, we parameterized upside down. Good news. The difference between these two possible parameterizations is just a minus sign. Right? Just like, in this case, the difference between parameterizing that way versus parameterizing that way, the difference between going that direction along the curve versus going that direction along the curve, it's a bunch of minus signs. That's it. Right? So likewise for surfaces. So all you got to do is heads up, after you compute your normal vector, look to see, did you parameterize right side up or upside down, the right way or the wrong way? If you parameterize the right way, cool. Congratulations, you got lucky. Proceed. And if you parameterize backwards, right, just say, oops, stick in a minus sign to recognize that I'm inadvertently going to compute the negative of the flux that I'm interested in, and proceed. You don't have to reparameterize and keep hoping one parameterization after the next that maybe you can parameterize it the right way. Just recognize the oops, fix it with a minus sign, and go ahead. Okay. All right, that's enough time on that topic. So now the rest is algebra. Remember, the merit of this formula for the parameterization is that it's already a pullback. It's just a matter of plug and chug. We computed n as a function of u and v on the previous page. F is a function of x, y, and z. X, y, and z are functions of u and v from our parameterization. Right? So plug it in. It's really just straight up plug and chug. And again, it turns into a double integral. Now, how do you compute the resulting double integral? We'll look chapter 14. There's a bunch of different possibilities, a bunch of different cases, a bunch of different techniques. You might do it in one coordinate system or a different coordinate system. This one works very well in polar coordinates. So, yeah, maybe that'd be a good choice. But the point is, it's just a double integral at this point. Okay. Be on the lookout for what I like to call geometric good fortune. You'd be surprised how often stuff like this comes up. Quick reminder, I know a lot of y'all are engineers. This is an engineering-oriented multivariable calculus class. In my undergraduate days, my second major was physics. I've done a bazillion, what I'm going to call engineering-relevant integrals, many of which were flux integrals. And I can report that in my personal experience, this kind of thing where the geometry makes nice things happen for you comes up a lot. It's extremely natural. The world is full of symmetries. The world is full of spheres and circles and planes, and which have nice symmetries, and so good stuff happens. So look, for example, for things like this. Suppose your surface is that. Suppose your vector field is this. Compute the flux. You can plug and chug, right? A lot of details there. Yikes. Lots of stuff. So instead of plugging and chugging every so often, just kind of heads up. Look for the opportunity to get lucky. Notice my entire surface sits inside of this plane. That means that everywhere on my surface, for the entire calculation that I'm going to be doing here, y is equal to 3. And if y is equal to 3, then that second component of my vector field is 0. And taking advantage of that, because that second component is 0, and because my normal vector points exactly in the y direction, my dot product is clearly 0. Answer to this flux question is 0. Pencil drop. No calculations necessary. No ugly parameterizations necessary. Just because of the geometric peculiarities of this problem, the answer is 0. Isn't that nice? So heads up. It's not always going to happen. It's usually not going to happen that it works out this nicely. But it is not rare, and it's well worth your time to just kind of take a moment and be like, hey, what do I know here? What freebies do I have before I start plowing through details? Okay. There's a big picture I want to talk about here. I've talked about some of this already. It turns out that the stuff that we're doing here in Chapter 15, all of the vast majority of the objects we're talking about in Chapter 15 are special cases of more sophisticated constructions. They just are. We're not presenting that point of view here because that point of view is too rough. It's too advanced for Math 212. It's not realistic. But even though we can't see those ideas, we can see the consequences of those ideas. So I can't show you exactly why it is that vector line integrals and vector surface integrals both are examples of integrals of differential forms, but we can capitalize on the fact that they are. Okay. So, for example, look at the analogies that we've already seen between fundamental theorem of calculus, fundamental theorem of line integrals in 2 dimensions, Green's theorem, fundamental theorem of line integrals in 3 dimensions. We've already got 4 theorems that all look exactly the same, morally, structurally, in terms of, you compute this, and you take a boundary, and then you compute the integrals, and oh my God, they're the same. 4 in a row theorems, that same exact structure happens. It's not a coincidence. Ultimately, that's because all of those contexts are studies of integrals of differential forms. Right? So the patterns that we've seen are consequences of this fact, that all of our integrals here are, in fact, integrals of differential forms. So what I'm about to show you is another consequence of this fact, that these two, again, seemingly different quantities, vector line integrals, we motivated from the point of view of work. Vector surface integrals, we motivated from the point of view of fluid flows. Seem very different. Right? But mathematically, there are a lot of patterns because they are both really, you get right down to it, kind of the same thing. Again, in ways that we can't talk about. So, what we can capitalize on, we can't talk about differential forms, but we can see all of the resulting analogies between these constructions. So, I have this page here that's made up to try to underscore all of the analogies, well, many of the analogies between these two constructions. So, for one thing, note they both come from parameterizations. Right? In both cases, we're looking for line integrals. We're looking at parametric curves. For surface integrals, we're looking at parametric surfaces. Okay. In both cases, the derivative of the parameterization gives us one of the relevant vectors. Right? This is straight up the derivative. This capital N, it was not exactly a derivative, but it comes directly from xu and xv. It comes from differentiation and a cross product. Okay, but anyway. Okay. In both cases, the unit vector pointing in that direction tells us the orientation of that piece of our domain. This t tells us the way that curve is going. This little n is telling us the direction that our surface is oriented. Right? The direction through which we're interested in flux. In both cases, there is a size that I'm interested in that comes from the magnitude of the dark green vector. How about that? Right? And in both cases, there is a differential vector pointing in that same direction that tells us both the direction and the size that we're interested in for that little piece. So look at the analogies. I mean, I like to do this with colors so you can see the analogies are very strong. It's the same picture with different geometry, but all the same relationships are there. And you can see here how those objects show up. What you might call derivative vectors are there and there and there and there. Multiplied by differentials from the parameter space. There, 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 there. The unit vectors. There and there. The sizes. D little s, D capital S. Right? And the orientation, the vector differentials there and there. The layout of these relationships is crazy analogous. And this is because, like I say, I mean, it's not a coincidence. It's not like, oh my God, these two physical applications just happen to algebraically lay out the same way. No, there is a single mathematical construction here called a vector line, called a integral of a differential form. Vector line integrals and vector surface integrals just happen to be special cases of those same things. And they just happen to have different physics applications. They show up in the real world in these different ways. And that gives rise to these different, but highly analogous, different representations. So, real quick, I know I'm out of time here, but chop it up, add it up, coordinate free, pull back from the parameterization, unit vectors, components. The analogies are super strong. So how I want y'all to use these facts is to take whatever it is that you understand in one of these contexts. Like, for example, the role that the velocity vector little v plays for vector line integrals. To whatever extent you don't understand capital N, think about that analogy. The capital N is playing a role in these integrals that is the analog of the role that v plays. So to whatever extent you understand little v, that should inform how you should think about and how you should organize your thoughts about capital N. And likewise everywhere else in this analogy. Okay, we're out of time. See y'all later. Have a good weekend. See you on Monday.